Okay, here we go. Oh, so that should be, yep. Okay, good. We should be good to go. All right. So class today is core essentials. First thing I have to do whenever I do any of these RSES presentations is fully disclose that these are the properties of RSES, Refrigeration Service Engineer Society. And Lori Shivo was nice enough to give me the rights to use it, and I appreciate that. So um, this is all theirs, and RSES is a great organization. So anyway, here we go. This is all stuff. If you ever take the NATE exam, that will potentially be on it. But again, NATE has a crap ton of different stuff on it, and that is a technical term. It is one crap ton of different things on there. So it's certainly not a presentation like this doesn't cover everything. But for all y'all, the students of the apprentice program, this is all going to be stuff that we've mostly covered, but we're just going to do review. So when I ask a question, be prepared to unmute yourself and answer, please. And then keep yourself muted if I don't ask a question. So here we go. All right. So, oh, hold on. I need to get my other screen up here so that I can. That's not the one I wanted to have open. Nothing like being prepared, you know. That's how I roll, though. All right. So this is all the stuff we're going to go over. I'm not going to read it all. You know, I can't stand reading slides. All right. So we've talked a lot about electrical diagrams, and the best way to learn how to read electrical diagrams is to read them. Quite often when you encounter a problem with any sort of equipment, the problem turns out to be electrical. We've talked about that a lot. But if you have a clear understanding of how to read a wiring diagram, then you're going to generally find the source of the trouble, especially if you're working on a piece of equipment you haven't worked on before. So we've talked about this before, especially when you get into commercial equipment where you have a lot more safeties or even things like furnaces. Anytime there's concealed wiring, where you have wiring that goes through, you know, any sort of a wall in the equipment where it's kind of hard to trace it from one side to the other, the electrical diagrams come in really handy. You're going to find a lot of different types, and we're going to review a couple of the different types and styles, but you're also going to notice that there's some key differences. So when you're in residential, you tend to rely a lot more on colors. Color code is a really big deal, but just keep in mind that electrical circuits don't care what color the wires are. They are colorblind, and in electrical, you can do that because you have fewer conductors, and so you can just use a couple different colored wires. But when you get into larger commercial equipment, especially really big stuff, like if you work in grocery store applications, you're going to find pretty quickly that the wire colors become almost meaningless because there's so many of them. And instead, they start to generally, if you're lucky, start to tag the wires with numbers. So pay close attention whenever you're looking at a diagram of any sort. If there are numbers, kind of like we talked about before with the design of different types of pressure switches and overloads and all that, you can learn a lot just by looking carefully at what it looks like. You know, for example, the close on rise type, the, pressure activated, double pull, single throw, et cetera, et cetera. You can learn a lot just by looking carefully at it. And the same thing is also true when you're looking at the numbers on it. So again, the biggest thing that I want you to overcome early on when you are doing electrical in terms of electrical diagrams is this feeling that you need training before you can start referencing them, because your training is referencing them. Obviously, we're covering the basics. We've already talked a lot about how to handle, work around electrical safely and the proper PPE and all that. Once you know that basic stuff, then it's just a matter of applying it and, tracing the physical wires through a piece of equipment using the wiring diagram. All right, so components of the wiring diagram. We've talked about this quite a bit. These are the components of the electrical circuit. You'll notice these first four. Power supply, so you have something that supplies power to the circuit. In the case of the high voltage electrical in our equipment that we work on, it's generally going to be 120 volts, 208, 240, up from there. But then the low voltage side for us is often 24 volts, and those are both considered our power supplies. And we talked a little bit about how a transformer is both a load in the high voltage circuit, and a power supply for the low voltage or the control circuit. Again, talking about, kind of typical residential electrical. Path for power, that's what we call, in our previous class, that's what we called our conductors. Our loads are the parts in the circuit that are the, you can call it power consuming. We've talked about this before. It's not really consuming power, but they're the part that take the electricity and do something with it. And so those would be things like, motors and lights and heaters and anything that takes electricity and changes it to something else. Electromagnets being a huge part of what we do in both motors and solenoids and all that. And the switches are another type of power passing device. In addition to your conductors, your switches are also power passing. And then on a wiring diagram, you also have the legend. And the legend helps to describe what's going to be on the diagram, what the different symbols are. And you'll notice pretty quickly that there are some kind of standards for wiring diagrams, but there's actually a lot of variation too. And so different manufacturers, different commercial versus residential versus industrial, depending on the complexity, there's a lot of different styles, but then also there's a lot of variation even from manufacturer to manufacturer. So getting used to some of the basics, but then looking at that legend or key every time is really helpful. It's one of the first things I'm always looking for. A couple different types of diagrams: ladder, pictorial, also known as point-to-point, and installation diagrams. Damien says he's here, but his internet is garbage. So, right. Ladder diagram is most commonly used. It's the one that we teach the most. It's the one that has, in my opinion, the most utility in terms of being able to diagnose things, because it's very easy to trace down. The downside of it, and the reason why newer technicians often don't like it as much, is that it does not physically show where the components are in the circuit. So it's much more about locating them in terms of the circuit path, not about locating them in terms of their physical position. Also, the components and parts and pieces and loads and switches don't look like how they look in real life, and so it makes it more tricky for somebody who's newer to the trade to identify them. But I want you to get to a place where you do that easily. It starts with the power supply down the sides, like rails of a ladder, and then all the loads and controls, loads and switches and conductors are placed in between them. Now, again, as you know, in real life, that's not how it works. In real life, a lot of times you'll have multiple conductors run together very closely in parallel. And so sometimes it's hard for newer technicians to visualize the fact that these two rails all the way on the outside are represented by just two conductors in a single cable, like in a low voltage thermostat wire or some 3-conductor wire or whatever the case may be. Now, keep in mind that this is the US standard, is to have the rails on the outside and the rungs in between. The European standard is to have the lines running down the center, often horizontally, and then everything branching out on the outside. And it's, a lot of people ask why they do it that way. It's because they just want to thumb their noses at us. We do it the right way, and they just want to do it different, just to be different than us. And no, actually, I have no idea why that is, but there must be some reason. It's the same reason they drive on the left side of the road, apparently. All right, so example of a ladder diagram. Let's go through a couple things. I'm just going to point on the screen. You should all be able to see my mouse. I wonder if I can make my mouse bigger. I don't know if I can. Yeah, I can. Let's see if I can make it bigger. I can actually I can do a laser pointer. That's cool. Oh, look at that. Hey, good old PowerPoint. All right, so let's start here. Let's start right here. What do we got right here? The thing I'm circling. I'll settle for any one of you answering. Everybody's
contactor.
Whoa, everybody at once then. Wow, that's awesome. All right, yeah. So it's a contactor. And what would we call this? Would this be a load, a switch, a conductor?
Switch.
This would be a switch.
Switch.
All right, somebody's got a really bad connection there. That would be a switch, yes. Because this just opens or closes. Now, in the position that it's currently in, is it open or closed?
Open.
It is open. Yes, it is open because there's a gap, an air gap in between. If it was closed, we would have a slash across, kind of like this little guy right here, this little C1 feeding our crankcase heater. All right, so let's pick something else here. What is this guy right here? The straight line and then the curved line. What is that?
Pressure switch.
Capacitor?
That's a capacitor. Yep, that is a capacitor. That's the symbol for a capacitor. And you can also tell it's a capacitor because of where it's connected in the circuit. It's connected over here
Man,
to our
it says
start terminal.
caps, that's why I said it.
Yeah, well, that makes it easy, right? And you knew it wasn't an actual cap, so that's good. All right, let's see what else. See what else we've got down here. What do we got right here?
Transformer?
Wheel.
Yep, we got a transformer, and the transformer is a load in the high voltage circuit. So this is a load path, right? L1 to L2 through the transformer. But in the low voltage circuit, it is what?
Power supply.
It is the power supply. So it supplies power to everything. You can see this side here is going over to R, going through our different switches. Let's say, now we already covered this, so let's see if any of you remember this. Somebody's got a lot of background noise going on there. Let's see if I can figure out who it is. Let's see. I think it's probably Mario. No, it's not Mario.
Oh, we need. Okay, is it better now?
No.
No, I can't even find you. Hold on. This is the beauty of. There we go. There you are. Yep. Because if you're muted, then it wouldn't be better, you know, because I wouldn't be able to answer your question. Okay, so here we go. This one right here, this one that says TC. Let's see if you can tell me what type of switch that is. So I already gave it away. It's a switch, but then what specific job is this switch doing?
Close on right.
Open on a rise.
It's not open on
Close
rise.
Close on a rise.
Yeah, because it's already open. When it rises, it's going to close. So is this switch normally open or normally closed based on how it's drawn?
Normally open.
Normally open.
Normally open because it's drawn as open. It's close on rise in what though?
Temperature.
Temperature, right. And so based on just looking at this, what do you think this switch is?
Thermostat.
Yeah, it's a thermostat. It's the cooling switch on the thermostat. Thermostat cooling. Yep. And so when the temperature rises, it closes and turns on our compressor contactor. Right? Make sense? And if we were to trace it down, this would go here. Let's see here. Where's our Y? Y goes here. That's kind of interesting how they have that drawn. Anyway, I'm not going to get caught up in the weeds there. All right. So what is this right here?
Low pressure switch.
Low pressure switch. Yeah. And so it is what type of switch specifically?
Uh-oh.
Normally what?
Normally closed, open on.
Open on
Drop.
on fall. Yeah. Open on fall. Yep.
Yeah.
Yep. Very good. Let's see here. We've got this little symbol right here. I don't know if we've talked about this one. I think we have talked about it before, but what is this little symbol? Anybody know?
Ground.
Yep, that is a grounding symbol, the universal grounding symbol. I don't know if it's universal. I'm not sure exactly what grounding symbol they use on Mars, but at least on Earth, it's what we use. All right, we're gonna keep moving on. Y'all did pretty good on the quiz. Some of you are just kind of cruising. Somebody says they can't see anything. I hope everybody can actually see what's going on the screen. That would be really disappointing. Let's see. Hold on 1 second. I just want to make sure. No, I know everybody because it's something with your set. You guys can all see what's going on my screen, right?
Not a thing. Just been guessing.
Yeah.
Yeah. Okay. I guess that's pretty obvious that you have been. For some reason, you know what it is that he set his screen to only show me just because he likes my face so much. That's what I think it is. Makes sense. Okay, here we go. Always the consummate professional. All right, let's see if I can. Oop. Oh, I see what's happened here. All right. Pictorial diagrams. So pictorial diagrams, second most common type. And the drawings more closely resemble the components themselves rather than symbols. And so they kind of give you an indication of the positions of where things are in the control panel or where they physically are in the system in some cases. And there's a lot of variation in how they are represented, but we're going to do just a couple quick examples of what those look like. So you can see right away that one of the biggest things that's different is that you don't have the advantage of the ladder setup. So things aren't just connected between two sides. you kind of have to trace them down visually. And so in terms of the tracing part, it's more difficult, but it makes it look a little bit more like it looks in real life, especially like if you look at that transformer, that looks a lot more like a transformer, right? I mean, it's, physically looks like a transformer. To be easier to recognize these wires using this diagram. But it's still a little more difficult to trace down because now if you want to see where this goes, you kind of have to do this weird little dance in order to figure out where it goes. But the relay looks more like a relay. Pressure switches look more like pressure switches. The compressor terminals look more like compressor terminals. Everything. So that's obviously why people who are newer prefer it. All right, installation diagram is the next one, and it's really just showing you field connections. So just things you need to do specifically in order to install a new piece of equipment, which is one of the big things that kind of drives me nuts about our trade is that we sell these boxes, and these boxes, condensers, air handlers, they have these terminals that people have to hook up. And a lot of folks, especially those who have just done a lot of installation, they start to think that connecting those wires is the only job. But the goal, of course, is to understand not just the wires where you make your field connections from the new box, but understanding everything else that goes in it, because otherwise you can't understand how to actually repair the machine. You only understand how to hook it up initially. And so that's why a lot of folks who have installed equipment their entire lives still don't understand how to diagnose electrical, because it becomes about connecting red to red and green to green, and not really about understanding where does that go once it hits that R terminal, or once it hits that G terminal or that Y terminal, and what feeds it and what is the sequence of operation. But in terms of being a practical thing to reference when you're installing a piece of equipment, it is a very handy thing, obviously, to look at. And sometimes there's going to be additional information there. So first off, you see here, we've got our little ground symbol there as well. So that's pretty universal. Whenever there are dashed lines generally indicate field installed conductors. And then here it also tells you, what size gauge wire to use. So sometimes there's just some additional helpful information. And again, in terms of the things that I see people miss most often, it's these little things that seem like they're throwaways. So your attention doesn't go to them right away. So for example, see where it says TB1 here? See if any of you can guess what that means.
Terminal block 1.
Yeah, terminal block 1, exactly. And now as soon as you notice that, well, now you can't unsee it. It's like, oh, okay, so now I'm looking for terminal block 1. And when you reference this same terminal block on the pictorial or the ladder diagram, now it's going to become a lot more evident. Which is a nice little thing. So anyway, just various little things to pay attention to. I'm going to check one thing real quick. I just want to make sure that we're okay. All right. That's right. I have to hit this button here. All right. All right. So when you're looking at the roadmap is the diagrams. You got to understand the symbols and signs. We've talked a lot about those already, and we've already covered some of those. But you want to understand what they are typically, and then you want to know how to find those answers on that specific diagram. And so again, refer to the key, but we're going to do this as a little bit of an exercise together. All right. So wide range of power supplies. Notice right away here that this is showing you where a field connected power supply is, right? We got the dots, but it also gives us some more information. So what is the voltage of this assembly over here? What is the designed voltage?
208.
Okay. But what do those other numbers mean? 208, very good. What do those other numbers mean?
Single phase
60 hertz.
Single phase 60 hertz, right. And so what other types of motors could you potentially run into? Or what other types of appliances could you run into? You could run into three-phase.
Single-phase motors.
Yeah, you could have this could say 3, that would mean 3-phase. This could say 50
hertz,
which would mean 50 hertz, right? And you'll run into that sometimes where some will be 50/60, where they could be either. But sometimes you literally have an incorrect product. You have something that is not designed for the power supply. It's not going to be common for you to find a 50 hertz, device, but it can happen. Something, especially if you order it off of Alibaba or something, and it's coming straight from overseas. Sometimes you will get a appliance or a some sort of a tool or something that isn't designed for our power supplies. So it is something to watch for. This one right here is 460, 3-phase, 60 hertz. Now, just while we're on the topic, anyone care to remind me what hertz means?
So how many times that flashes in a minute?
So how many cycles per second?
Cycles, that's right.
Yep.
many
And that's the
cycles?
sine wave, that we talked about. How many times does it make a cycle per second? And 60 hertz, 60 cycles is the standard for the United States. Now, what's another term for that, though? What's another term for cycle rate? Well, it's
Frequency.
frequency. Sal answered it in the chat. Frequency. So yes, that's another term for it. All right, we're gonna keep going. I always like to nitpick these things apart. I never just follow what the people who make the slides intend. But that's me. I'm a rebel. I'm a rebel without a cause. Actually, I have some causes. They just might not be good ones. All right. So most schematics use straight lines to represent the wires and connect components. Often different lines will indicate different types of wiring. So just pay attention to how the lines look: thinner lines, thicker lines, dashed lines, solid lines. Those are generally going to represent something. Now there are cases, and let's go ahead and move ahead here. There are cases where wires will have little curves in them, but usually that doesn't represent anything other than just to show wires that do not connect versus wires that do connect. So when you see these little points here, that's an indication that there is a connection there, generally speaking. And then if there is no dot in a straight line type of wiring diagram, then that would indicate no connection. So connection with dot, no connection without dot. Another thing to notice and pay close attention to is that, especially on contacts, a lot of times they are going to have numbers there, and those reference back. Sometimes you're going to find that even on the device, it will have numbers marked on it, and that makes it a lot easier to kind of find where you are in real space by referencing those numbers. All right. When we see the ones that don't have dots, though, you'll find that wires that do not connect will have these little jumpers. So if you look at this little guy right here, this is a connection. Connection, connection, connection. These ones that jumper over are not connections. And there is no real jump over in real life. It's just a way of showing that there's no connection. That makes sense to everybody? It's pretty straightforward, but yeah, we would call these crossovers is a term that we would use. Just a way to visually represent these wires ain't connected together. All right, wire colors, standard wire colors on line voltage. Colored wires are generally going to be your hot lines. And again, we're talking about your standard residential sort of thing. When you get into heavier commercial, they'll have different standards for A, B, and C phases. Different voltages will also tend to, within a structure, if you have different voltages, they'll run different wires just to identify them. But we're just going to stick with the basic stuff like commercial, residential here. So when you have black wires that are black, wires that are red, those are going to be your ones that are line voltage. If you have white wires, that's going to be neutral. And green wires are going to be ground. Green or bare are going to be ground. If you, just in terms of electrical, if you ever are working with like two conductor wire where you're using a white wire as a current carrying conductor, you need to make sure that you phase tape it well up the wire. Now, again, this is an electrical thing, and I'm not teaching electrical code here, but just in terms of identification, people, when they visually see a white, they'll assume it's a neutral. So if a white is not being used as a neutral and is instead being used as a true hot current carrying conductor, then you should phase tape it up the wire with black tape or red tape or whatever. And the codes, I think, have recently changed about that too. So I'm not telling you current NEC codes. I'm just telling you what a good best practice is. Low voltage, red is 24 volt power. White is generally heat. This says yellow is cooling, but we talked about this. Yellow is cooling on a straight cool unit, but it is actually what on a heat pump? What is yellow on a heat pump?
Contactor.
Mm-hmm. Compressor contactor. Yep. And what is the standard color code for the reversing valve?
Orange.
Orange.
Orange, right. And
Unless
then green.
it's a ream, it's blue.
Unless it's a ream, then it's blue. I don't know that all reams are. Maybe they are. I had a conversation with with somebody about this recently. Anyway, but yeah. So green is, it says fan, but green is blower. Orange is a cooling call for reversing valve, and blue is a heating call for reversing valve. And that's Rheem is one of the companies that use that B terminal, which confused everybody and whatever. All right.
And then blue is common.
Blue is common. And blue being common is one of the least set in stone, because you will see black being used as common in some cases too. And again, none of this really matters. You can use any color for any one of these purposes, but as a standard, we want to use the standardized colors. And as another note, just to complete aside, if you're ever splicing wires in an 8-conductor thermostat cable, you splice all 8 wires, regardless of if you're only using 4 or 5. You splice all of them always, because you do not want somebody else to come along and try to use one of the different conductors and then find that it's broken because you forgot to splice it. So always splice all of the conductors, whether they're being used or not. Make sense? Of course it does. Moving right along. Some manufacturers will mark drawings to indicate wire colors. So some are going to tell you what color the wires are. Don't count on that. They're not always going to tell you, but often they will. And this is a common way that they'll do it. Talking about switches, we've already talked about this a lot, but it's worth reviewing. Switches open and close the path to complete the circuit. So they close the path to complete the circuit, to make the circuit, to power the circuit, to energize the circuit, whatever term you want to use, and they open to break the circuit, to open the circuit, to prevent electrons from moving, whatever term you want to use. No matter what metaphor you pick, it doesn't work perfectly. I used the metaphor of the drawbridge, which somebody didn't like. Rapcan didn't like my metaphor of the drawbridge, but the drawbridge, when it's open, the cars can't go through, but then somebody pointed out, yes, but the boats can. You know, I just can't win with my electrical metaphors. So you just have to memorize it. You know, if the switch is closed, then the electrons can move. If it's open, they can't. Switches can be activated by a variety of things. We've mentioned a few, pressure and temperature being some of the most common that we run into. You can have switches that are manually activated. It's also very common. So, and then some switches use compound logic, where you have multiple things have to happen for a switch to open or close as well. Call those super combiners, where you're combining more than one thing in order to create a particular action. We do that all the time in grocery in order to initiate a defrost or whatever the case may be. You have multiple things going on at once that change the system's operation. That's it. That was in there for you, Chad. A little super combiner reference. And my wife is taking a picture of me. Bryn's looking at me through the glass there. All right, so switches can have single or multiple poles. Poles would be the number of contacts. This is where it gets really, it gets kind of confusing, because the way I like to think about it is in terms of, I like to think of the pole as being the part that connects through it. That's one way of thinking about it. But however you think about it in order to get the answer right, that works for me. So we've talked about this already. Let's see here. All right. So these are schematics of showing switches in the closed position. So this one not used as much in what we see in residential, but that indicates a closed switch, a normally closed position. This one indicates a normally closed contact. We also have a normally closed switch here. And then open switches, normally open, normally open, normally open. All right, so single pole, single throw being the most common. Single pole, single throw, normally closed. Single pole, single throw, normally open. Single pole, double throw, so it can throw in multiple directions. And that's how I think about that. So I think of this, again, as my pole, and it's throwing into different directions. And then double pole, double throw, you have 2 sets of poles, and each one has double throws. And that's kind of, because some people, when they first see this, think, well, I actually have I actually have 4 throws. Well, no, it's still only double throw per pole. So anyway. Any questions about any of that before I move on?
Yeah, what are you going to use the double throws? What would that be inside of our units?
Yeah, so like this double pole, double throw that we show down here, that would be a very common 9340 relay. And a 9340 relay can be used for multiple different applications, but you can use it for the one that they often use as an example is lockout circuits, which we haven't gotten into yet. And I'm not going to explain that exactly. Those aren't really that common anymore, at least not for what we see in equipment. But for example, you could have even just something as simple as an indicator light. So an indicator light is normally on, and then it goes off when something else changes. There's a lot of different reasons why you might want to use it, and the most common reasons are actually weird things that we come up with in order to solve particular problems that we're having with a piece of equipment, where we're combining two different things together. So a really common version of a single pole double throw would be a 3-way switch in a house. That would be like a really common application. So in the case of a 3-way switch, you would take 2 3-way switches, 2 single pole double throw switches, and you would connect the throw sides to each other, and then you'd in and out, and that's how you get that effect of where either one can turn the light on or off. That's the most common example that we see. And another case where we use these types of single pole double throw designs are when we're wiring up heat strip interlocks. That's another common one. And again, that's from the factory. They wire them that way. And so it allows it to automatically bring the blower on whenever the heat is on. I have a whole 9 panel on how that works. It's not easy for me to explain just showing it with a picture like this. But there certainly are cases. I mean, the majority of what we're going to do is going to be, so most commonly we're going to see single pole, single throw, or double pole, single throw. So like a standard 2-pole contactor is double pole, single throw, rather than double pole, double throw. Does that answer your question? I could just keep going. Okay.
It works.
Whenever you ask questions, I just talk until you all get tired. And just say fancy words, and then you be quiet, and then I can keep talking again, which is great. It works perfectly for me. All right. So yeah, more examples. Double pole, single throw. That would be our typical double pole contactor. It's going to look like this. Double pole, double throw, and we have normally closed, normally open. You can have all kinds of different configurations. This is a 3-pole single throw. That would be a standard 3-pole, like a 3-phase contactor. Just as an aside, where we can use what we call a +1 contactor. Everybody's seen these, where you have a contactor that's got what has one set of contacts on it, but then the other side is just a straight pole on it. So it's really only a single pole contactor. Whereas we can use that in residential. In 3-phase, you always have to break all 3. Because if you don't break all 3 in 3-phase, that motor will still try to run. And that's something that we call single phasing. So in 3-phase applications, you're always going to be breaking all three legs. I say always. Whenever I say always, there's always some exception to always that I'm not thinking of. And somebody be like, well, actually, there's this whatchamabobby that does use thingamajiggy. And I'm like, oh, dang it. So I always have to call that out. But anyway, you got to break all 3 because you don't want a single phase. You don't want to just run on 2 legs. All right, so in this illustration, and we got a pair of safety switches. RS2 is a temperature safety. You can see that. We've talked about that before. And AFS2 is a pressure switch. So this is a normally closed. Actually, so let's say the whole thing. Single pole, single throw, normally closed, open on fall, pressure activated switch. Right? So I did one. One of you do the next one. What is this? Anybody want to take that on?
Single pole, single throw, normally closed, open on a rise.
What?
Switch.
Yes. Nailed it. You've done it. By golly. I'm so proud. Never been a prouder papa. Oh boy, there's Potato Man again. Oh geez. It's terrifying. All right. So on this one, we've got a single pole double throw temperature activated. So it's normally closed in one position and normally open to the other position. And so that's where it kind of gets tricky, is that a switch isn't always just normally closed, normally open. In this case, it's normally closed to the bottom position and it's normally open to the top position. So as the temperature rises, then it's going to make to that top. And this would be a limit switch or a fan control. It's sort of an old school way that we used to control furnaces was through what we called a fan limit, which was a really cool thing that was still out there in our market when I started in the trade. I'm sure Jessica's husband has worked on some of these fan limit switches. Not saying that you're old or anything. I'm just saying you've probably worked on a fan limit before. He sure has. See, there you go. There you go. Good old natural draft furnaces. I mean, there's nothing better than some natural convection. Who needs these dad-burned inducer fans? You know what I mean? You know what I'm saying? You hear me. All right. So that is it before break. We're going to go ahead and take a quick 15-minute break, and I'm going to end the YouTube live stream. That was just a quick little look in for y'all. Thanks for watching. And this is the sort of stuff that we do 2 times a week. Don't usually do it on Zoom, but we're right before Thanksgiving, and we are true believers, warriors, really. I mean, really warriors. I mean, you know, let's be real honest. Doing 2 hours on Zoom, that is just absolute killer stuff. So anyway, thanks for joining us, and we're going to take a 15-minute break now.